RC circuits. A resistor capacitor, otherwise known as an RC circuit, is a circuit composed of resistors and capacitors that are connected to a voltage source. This is the symbol for the battery here that's shown sometimes, as opposed to we've used this certainly, and we've actually used this. This is a capacitor, right? We've shown it like that, and this is a resistor. Here's the switch. We have a circuit with the battery, a light bulb, then a junction where we come up to a capacitor. We have a switch. There's another light bulb here. Notice how we switch to using the direction of conventional current flow. We're coming out of the positive terminal this way. Let's start with the switch open. There's no current in this branch, right? There's no complete path for current to flow. So the current flows just as indicated by the red lines here around this loop. So what's in the circuit? We have a battery, two light bulbs, each with a resistance R. So when we find current, current is equal to voltage over the equivalent resistance. And what's the equivalent resistance of two resistors in series? Well, that would be 2R. So that's our current coming out of the battery. Now close the switch. Immediately after it is closed, there is no resistance in the branch with the capacitor. Remember, we don't have any charges on the capacitor yet, so there's no potential here opposing the flow of current. This looks like something called a short circuit. There's no resistance there at all. So the current flow is now through this light bulb, comes up this branch, and down here. So what happens to the current coming out of the battery when we close the switch? Well, current, of course, is Ohm's law, V over R. This light bulb is not in the circuit, so the only resistance we have here, current is V over R. So what happens is we have more current coming out of the battery, and this light bulb here will get brighter. The current will increase in the first light bulb, so it gets brighter. But none of the current is going through this light bulb now, so it goes out. A long time after the switch is closed, and we'll deal with what that time is when we get to AP Physics C, this capacitor is fully charged and there is no more current in the top branch. The rest of the circuit behaves as if the capacitor were disconnected. Therefore, the current through the battery and through the two light bulbs is now back to its original current of V over 2R. So at the end of this procedure where we close the switch, the first bulb is going to return to its original brightness, and the second bulb, which had turned off, now starts glowing again and returns to its original brightness, which is the same as this light bulb. A 3 millifarad capacitor is connected to a resistor with a resistance of 2 ohms and battery with a potential difference of 6 volts. How much charge is stored in the fully charged capacitor? When fully charged, the voltage between the plates of the capacitor will be the 6 volts here. Why is that? Well, no current is flowing. So if you use Ohm's law here, V is equal to IR. That means no voltage is across the resistor, so it all has to be across the capacitor, all 6 volts. So we change the capacitance from millifarads to farads by moving the decimal place over 3 places. The voltage is 6 volts. Here's our capacitor equation. We need to solve for the charge, so we multiply both sides by V, substitute in our givens, and we get a charge of 0.018 coulombs. So the key part of this problem was recognizing that the entire voltage drop is across the capacitor once it's fully charged. What is the voltage across the plates of the capacitor if it is fully charged while the switch remains open? The answer is 6 volts. And why is that? Since the capacitor is fully charged, and you've got this open switch here, there's no current flowing in the circuit. Hence, no voltage drop across the resistor, right? Because V equals IR. All the battery voltage is supplied to the capacitor. So as the switch is remaining open, no current flows through the upper portion of the circuit. So essentially, you have a circuit with a 2 ohm resistor and a 3 millifarad capacitor and the battery. There's your circuit, but there's no current flowing because it's fully charged. The switch has been closed a long time. What is the voltage across the plates of the capacitor if it is fully charged while the switch remains closed? When the capacitor is fully charged, no current flows between points A and B. You can see we've grayed out the capacitor here. Essentially, the circuit looks like two resistors in series. The voltage across the capacitor's plates is the same as the voltage difference between points A and B, which is the same as the voltage drop over the 1 ohm resistor here that it's in parallel with. Continued on the next slide. Find the circuit resistance of the 2 ohm and the 1 ohm resistor. Well, they're in series, so we just add them, so we get 3 ohms. Find the circuit current. We use Ohm's law, voltage over R. The voltage here is 6. 6 divided by 3 ohms is 2 amps. And finally, find the voltage across the 1 ohm resistor, which will be the same as the voltage across the capacitor, because they're in parallel. So that's IR, 2 amps times 1 ohm, 2 volts. The switch has been closed a long time. How much energy is stored in the fully charged capacitor? We convert the capacitance from millifarads to farads by moving the decimal point over 3 places. Right? 1 millifarad is 10 to the minus 3 farads. Now, in the previous example, we calculated the voltage across the plates of the capacitor to be 2 volts. So we're not going to do that again. You can back up and see how we did that if you'd like. And the energy is 1/2 CV squared. Here's the capacitance. Here's 1/2. Please make sure you square the voltage, and you get 0.006 joules of energy storage.